All right, everyone. So welcome to our first fully virtual GeoFlow meeting. We have a wonderful lineup of speakers. I hope everyone's doing well and hanging in there and enjoying the physics while you can. So I'm going to hand it over to Masamichi, one of our GeoFlow postdocs at Berkeley, and he's going to introduce the first speaker.
Okay, so we are very happy to have Charles from MERA, and he will tell us about conformal field theory, magical. Please start.
Right. Thank you very much for the organizers for having me, and it's great to meet you all virtually here, and hope everyone is staying safe and healthy. So I will start with this, I guess what Ning would call a trippy title. Conformal field theories are magical. So this is joint work with Christopher White, who is a postdoc here, and Brian Swingle. So great. So as a brief outline, let me first motivate. Why do we care about this kind of questions? And you might be wondering what exactly is the magic I'm talking about. So after motivating the problem, I would talk about what is magic and how we can compute magic in a conformal field theory, at least in this sort of a preliminary setting. Then at the very end, I'll use MERA tensor networks to explain some of the features that we're seeing, so that we gain some intuition after seeing the data. So as we're learning more and more about building a quantum computer and the theories of quantum computing, we're starting to think more about what would happen if we actually have a quantum computer and what kind of problems we would like to solve. For example, one problem we would like to solve on a quantum computer is that we probably want to simulate quantum field theory on a quantum computer, perhaps strongly coupled field theory and like QCD in the confining phase. But before we even get there, there are many stepping stones we have to, stepping stone questions we have to solve. And one of them is for example, how do I even prepare an initial state on a quantum computer that's interesting, right? For example, you want to prepare a ground state of a field theory. What kind of gate set would you have to choose, right? How many gates and how do you place them in a circuit in order to construct a state like that? And how hard is it to implement these gates in the circuit? And can we do it with fault tolerance and so on and so forth? There's a lot of questions we have to answer. But I think for this collaboration, there's also a very strong motivation coming from holography or from quantum gravity. A part of this is also related to state preparation in a sense. For example, we would like to understand how to prepare a ground state or some geometric state of a holographic CFT. So in the past decade, we have learned a lot about how tensor network is a very powerful tool. It can be used to construct very geometric and very simple toy models for these kind of holographic states. For example, the happy code, I guess this is called a holographic state, but I probably would just call it the perfect tensor state. It reproduces the RT formula, or happy code itself. It has this error correction code property that's very similar to what we expect in holography in terms of subregion duality and in terms of entanglement wedge reconstruction. And then, of course, there's also random tensor network. It gives you a lot more flexibility. They do reproduce a lot of the features what we expect in holographic states. Nevertheless, they don't reproduce all of the features. Some of them are really important. For example, they don't reproduce the kind of correct entanglement spectrum of the CFT ground state. Neither do they have the kind of power law decaying correlation. Right. So the question really, I guess, from the gravity point of view now is that we really, I mean, from a field theory perspective, it's important to understand the conformal field theory, how to prepare the theory on the tensor network, perhaps with the correct entanglement features and so on and so forth. From the gravity point of view, we also like to understand how this tensor network is tied into the bulk theory, and constructing better models in tensor networks, and perhaps approximate quantum error correction models will help us do that. Now the question is, we're here, right? We have these models that have some features, like it produces the flat spectrum for a conformal field theory ground state. So what additional ingredient do we need that's both necessary and sufficient that will get us from where we are now to where we would like to be, right? So the answer to that question is magic, right? You need a lot of magic to do that, and this is the focus of this talk I would like to emphasize. So before you turn off your Zoom and dismiss me as a crackpot, let me just take some moment to explain what magic is and where it comes from. Not by just, yeah, anyway. So let's first take a little detour and ask the question, what makes quantum computers so powerful, right? So for example, we have the Shor's algorithm, we have the Grover search, there is quantum speed up, at least as far as we can tell. So where does that come from, right? So for example, if I were to give you a set of gates, or a set of unitaries, really, that you can use to construct your quantum circuit, let's say the set of unitaries are the so-called Clifford unitaries, which are basically unitaries that maps Pauli operators to Pauli operators under conjugation. So in the cubic case, right, when you have regular Paulis, really you just map Paulis to Paulis up to the side. But it can also, there's also, this definition also works for a generalized Pauli group. So for example, you can have these clocks and shift operators and so on and so forth. So then there it will be up to a phase. So the Clifford group, it's sufficient to generate a tensor network like the happy code, for example. So it's already powerful enough to construct some of the models we know. So for instance, again, in the cubic case, just so that we have some footing, it's generated by, for example, a Hadamard transform, which takes a qubit in the 0 state to a superposition of 0 and 1. And then there's a phase gate, which adds a relative phase pi over 2 between 0 and 1. And then there's a C0, which generates entanglement, right? So these are already doing a lot of things we would consider quantum, right? But there is a theorem by Gottesman and Cannell that says that if you only have Clifford operations like the ones using these gates, it does not provide you with any quantum advantage. In fact, you can simulate these the actions of these circuits perfectly well with the classical computer with polynomial time, right? So it seems that, okay, if you really want to exploit the full power of a quantum computer, entanglement is not enough, right? You have C0. Neither is superposition is also not enough because you have Hadamard, which generates superposition. So it sort of seems like a naive question. Then what does make quantum computer more powerful, right? It must be magic, right? So this is sort of the term where, at least as far as I understood, where the term magic first came from, is sort of like in the context of quantum speed. Now, but those of you who are already familiar with quantum computation already noticed that hey, Charles, the Clifford group is not a universal gate set, right? You can't really get to any state that you want from, for example, a product of 0 states. In fact, what you can do with the Clifford operations is that if you started with a bunch of 0 states, like this one, you can only turn it into a stabilizer state, which is a proper subset of all quantum states. And in fact, it is a perfect tensor state, or the holographic state. The tensor network that I showed earlier is actually a stabilizer state. So it has the flat spectrum, is not really what we need for conformal field theory. However, we can supplement this Clifford group with one extra element, this T gate, which is basically a pi over 4 phase gate. And once you have this, it was shown that the Clifford plus T gate set is indeed universal. which means that you can implement, for example, the short algorithm with this set of gates. And these gates are enough for you to exploit the power of all these very nice quantum algorithms. And hence, people tend to think, well, although maybe not entirely correct, is to say that maybe the T is what brings the magic to the quantum speed. So it's sort of, the notion is kind of stuck as far as I can tell. So so there are many definitions of magic, but most of them is referring to is sort of measuring how non-Clifford the circuit is, or how far it is from a stabilizer state, right? The kind of states that you can get from Clifford operations. Or it's sort of measuring the kind of T-ness, how many T gates do you need for this operation, or how many T gates can I extract from the state? So this is the overarching and intuition behind what we call magic. Of course, I would like to point out that really it's all these gates working in synchronous that gives us the power of quantum computation. Right? If I were to take out C naught, obviously you wouldn't be able to do anything. So really you shouldn't be thinking about, oh, it's only the T gates that's bringing the quantum speed up. But the terminology is a terminology. So this is what we mean by magic in this talk.
I had a question.
Yes.
I understand that the T gate as a magic resource is kind of like the industry standard, but it doesn't have to be that way, right? Like it could be basically any gate that's not stabilizer, and it's not clear that is there any like a theoretical reason why the T gate is more optimal than it is, like the best possible choice compared to other non-stabilizer gates?
No, I don't. So correct me if I'm wrong here, because I'm not an expert on this, but I don't think so. As far as I know, indeed, as you said, you don't have to have the T gate. Any gate that's outside the Clifford group works. So I don't see why it has to be that way.
Yeah, I guess
the reason that T gate is treated as a resource oftentimes is because Cliffords can be implemented efficiently with fault tolerance, whereas T is trickier. So
yeah, but you could say the same thing, I think, about any. Yeah.
So I don't think T is so much more special than the other ones.
Right. So I guess my point is just that this definition of T-ness as a quantification for magic is a little bit gauge dependent, right? Because you can choose many different choices for your state. Sure. Like I could have picked
sure. Yeah.
That
yeah. Yeah, absolutely. It's like there is a bazillion of different definitions, but mostly a focus on non-Clifford, non-stabilizer.
Well, I think possibly a way to frame this is instead of T, I could choose T combined with any combination of Clifford gates, and that would equally well be a universal gate set. So maybe the question Ning's asking, or a way to reframe it, would be: is there a notion of like orthogonality to the Clifford algebra, and is T in any sense orthogonal to all the Clifford gates?
But I think what I was trying to say is that you can take any element doesn't have to be this one, right? You can take any element that's outside which is orthogonal to the Clifford.
Yeah, of course.
So all of that works will give you a universal gate set. So it's nothing special about this one. Okay, so.
Hey, so one further point. T is a nice thing. A T gate is a nice thing to talk about to get a handle on the situation. It's a concrete gate, right? But there are measures of magic that abstract over, what gate exactly you mean. And we're actually going to go use a more robust measure.
Yeah, exactly. Which is something that I'm going to talk about. Yeah, thank you, Christopher. Okay, so. Great. So perhaps let me just talk about the different kind of magic. It seems like the most naive thing you can do is, suppose you have an optimal circuit that's prepared with the Clifford plus T, then you can probably just count the T. But as you as we all know, it's very difficult to prepare a circuit that you would call optimal, right? And furthermore, there's ambiguities in choosing, T as opposed to something different. So it's hard using this kind of first definition. Alternatively, you don't have to do that, right? You can measure, you can use the non-stabilizerness to measure a magic, right? So here, again, suppose you have a state that you would like to understand how magical it is, right? So you just measure the minimal distance it is from any set of stabilizer states by means of relative entropy. It's slightly better defined than the first definition. Nevertheless, it's still kind of hard to compute. So in this work, we actually use a computable measure. It's called MERA. There are different computable measures out there. They're efficiently computable. Nevertheless, none of them really, well, I would say they give you an estimate, right? They don't really compute this quantity exactly. So now now we have all the prerequisites out of the way. I would like to introduce the questions of how much magic really does a CFD ground state have. Before that, before we can answer that question, let's define what MERA is. This is the measure that we're going to focus on for the majority of this talk. Now, it's very easy to define it, right? So suppose you have poly elements of the poly group, right? So if you have, so this is all T sub U. If you have a spin chain, for example, where you have tensor products of different Hilbert spaces, and you can define generalized polys. You just take tensor products over these poly bases, and then you take equal superpositions over these poly group elements, and you can generate an operator basis like A sub U, right? So A naught is just an equal superposition of these poly elements. AU, the other elements, can be generated by conjugation between other polygroup elements, which basically would change the relative signs and phases in this superposition. So after that, you basically have a complete set of operator bases, and then you just expand the state in terms of the spaces, right? And then you get a bunch of coefficients. And these set of coefficients, which depends on you and depends on the state that you are thinking about. These are called the discrete Wigner functions, discrete Wigner function of the state, right? And after that, all you have to do is to take the absolute value of these coefficients, sum them, and then log them. So this is the definition of MERA. Why do we choose it? Well, first of all, it's efficiently computable. As you can see, all you have to do is to list out these operator bases and then compute inner products, which is very very straightforward. It is intuitively, well, in terms of the properties, it sort of upper bounds this so-called distillable magic, right? So oftentimes you don't want to. It's hard to implement T-gates, right, in quantum circuits. So what people do is that they find out these states with magic, and then they act Cliffords on these states to generate what's equivalent to T-gate into the quantum circuit. So not all states give you very good result. So the ones with a lot of distillable magic is the one that will eventually give you very good fidelity of a T-gate. And this MERA sort of upper bounds that. It's not the very tight upper bound, but it's an upper bound. But it also has this additive property. So if you have two product states, each have a certain amount of magic, you do expect the amount of magic to add because they're product. And it's also monotonic under stabilizer protocols. So what this is coming from the fact that, in fault-tolerant quantum computation, the Cliffords are usually treated as free resources because, as we know, they can be efficiently implemented with fault tolerance and so on and so forth. Magic, on the other hand, the T-gates, they're the ones that are difficult. Right? So it's very much like in quantum communications. the LOCC operations are treated as free operations because you can just do them, whereas entanglement is treated as a resource because you actually have to work hard to get them distributed in the first place. So it's a similar here for magic. You expect that in the quantum communication story that entanglement to not increase under these LOCC or free operations. Here is a similar. You expect magic to not increase under these stabilizer or Clifford operations, and so on and so forth. So this is an important inequality which also satisfies. One oddity of this mana only works for odd-dimensional Hilbert space. This is some deeper mathematical result that I don't really understand, but it does give you the thing that you want. For example, it is exactly 0 for stabilizer pure states, because we expect stabilizer states by definition to have 0 magic, right? This reproduces that. Okay. So a lot of good properties of this measure. Now we talk about the model we use for conformal field theory. So it's called a 3-state Potts model, because magic, the mana measure only works for odd-dimensional Hilbert space. What's the smallest odd-dimensional Hilbert space? Odd dimension you can find is 3, right? So here this Potts model is sort of like a future version of transverse field Ising. Right? So you have some nearest neighbor interaction, and then you have some field, transverse field in X. So theta sort of controls the relative strength between these two terms, and they compete, right, in their effect. Like the Ising model, you expect there is a phase transition when their contributions are roughly equal, and indeed you find one that this is well known that there is phase transition at theta equals pi over 4, which is actually described by conformal field theory in thermodynamic limit. So this is the kind of theory we're going to use. And Christopher, who did all the numerics on DMRG, can tell us that all the details about how we can just find a ground state of say 128 site spin chain with this Potts model, and then we will be able to find a ground state using DMRG, or at least to very good approximation. And then after that, you just take the ground state there and then compute the magic, right? Because you have the states, you know the definition of mana, and then you just compute what it is. But it's not as straightforward as you would think, because as we've shown that you really need to do an expansion over all the operator bases. And if you have n sites, that's 9 to the n number of coefficients you need to compute, and then you have to take their absolute values and have to sum them up. At least in the brute force method, the complexity of this scales exponentially with the system size. So for the exact numerics that we looked at, the largest system we can compute was for 7 sites, or at least if you have a 100-site spin chain, we'll just look at a subsystem that has 7 sites at most. So here is a plot of one such mana that you would compute. So on the horizontal is the theta parameter that controls where the criticality happens. So criticality happens on this dotted line here. It's theta equals pi over 4. And on the vertical axis is plotted the mana of the subsystem divided by the number of sites. Right? So it's mana density, that what we call here. So 2 things immediately we notice is that as you tune the system to close to criticality, the mana density increases. And in fact, it peaks around here and then comes back down again. And the second feature that we realized is that as you take larger and larger subsystems, like so you have higher and a higher mana density, and it seems to have it will probably saturate at one point. So this tells us 2 things. Well, the first thing is obvious. It seems like something interesting is happening near criticality. In fact, the peak you shifted is due to finite size effect. And there's also, if this trend continues, somehow it, saturates near some point, then you expect a volumetric scaling of mana as a system size. So there are two immediate lessons that we learn. And in fact, you can also compare this subsystem mana to the total mana of a small system. So for example, you can compare the 6-site subsystem in a 100-site spin chain mana to the mana of a 6-spin system. And this is precisely the black curve that's plotted is the mana density of the 6-spin. So the spin chain only has 6 spins. And this is, it's actually, in terms of behavior, is very close to the subsystem mana that we're seeing here. And again, the peak is shifted because of finite sense effect. Right. So you can also, in fact, reproduce these sort of behaviors so that using mean field theory, right? Because computing mana exactly with the exact ground state, it's costly, but you can do a mean field calculation, and it gives you the general trend again, right? So these curves returns are mean fields one side, mean fields 2-side estimations, and you can see that indeed it kind of goes up and then it peaks around criticality and then comes back down. The blue is the exact mana calculation. So although they don't line up exactly, this qualitative trend is sort of is observed in using different methods. So so far it is the mana of a subsystem or the mana of the total system. But we can also look at mana of a subsystem where the sites are separated, so it's sort of non-local. For example, you can have a reduced density matrix that's on 2 sites, but these 2 sites are separated by some distance delta x, which is the site difference in the spin chain. Would like to ask you to focus here is the black line over here, which is at theta equals pi/4, was where the criticality happens. This curve is given by a power law, which is of this sort of behavior. So the red curves are what the fitted values look like, right? So what this tells us is that magic is also non-locally distributed, right? There is, in fact, magic over a longer range, and then it would just keep the power law decay behavior until it reaches 0. I will try to explain what this is later on with MERA. It gives you a very nice picture, but for now it seems like power law and then it hits 0, which is not at the system size, but roughly half of the system size, maybe 2/3 of the system size. So all of these interesting features. Okay. Good. So now we have soaked ourselves with all the data. Let's try to understand these data. So the tool we're going to use is MERA. Just to briefly remind you what it looks like. It looks like this, right? It has 2 sets of tensors that you use. One are these green triangles. They're called isometries. And you can contract them into identities and so on and so forth. And then there are these blue squares. They're disentanglers. They're basically unitaries that, at least in this network, they act on 2 sites. So in these MERA networks is that you basically tune variationally these tensors, the triangles and the squares. And then you can fit to a CFD ground state to a very good approximation. And now suppose you do that and you find out what the tensors are, the squares and the triangles, you realize that these tensors, which you can then turn into quantum gates, they're not Clifford gates, right? No surprise there. But each of them require a certain number of T gates to build. Now, we don't know how many exactly because we'll have to do the optimization procedure. But let's just say a square contains m sub squared number of T gates or units of magic. And let's say the triangles contain M subtriangle number units of magic, right? And then now, if you want to estimate how much magic has gone into this state, right? All you have to do is to count the total number of tensors in the MERA, and then multiply by this number, right? So it turns out that this indeed scale, the total magic of the system scales volumetrically, right? Where n is the number of sites in the station. We can do better than that, right? We can also use MERA to estimate subsystem magic, which is the one that we studied very precisely numerically. So for subsystem magic is slightly trickier because you have to determine, where information ends up. So for example, you have a tensor here. This tensor may contribute to the magic in this subsystem, but it may also contribute to the magic in some other subsystem that's way over here. So instead, what we use is that we're going to argue that the leading contribution of the magic in the subsystems, in fact, coming from these tensors in the so-called past domain dependence. These are tensors where information, no matter how you want to go out, no matter which path you follow, you can never leave this interval over here. So you can safely argue that all of the magic that's contained in these tensors kind of are preserved in this subsystem. And you can similarly just count the number of tensors in the subsystem, and you get something that looks very similar as the total system magic. Instead now it sort of scales as L. And if you take the magic at the critical points and then just plot them, so these are mana density at different L's, and then just plot them, and they give you these blue circles. In fact, the MERA expression, which you can write down exactly, fits them relatively well. Now, maybe you don't want to believe this, it has only 7 data points. Nevertheless, the fact that it also performs very well in this small subsystem size is pretty interesting. Now, you can also use the same tool in MERA to understand non-locally distributed magic. So for example, suppose you have a 2-site reduced density matrix. That's where the sites are labeled by the yellow pentagons over here. We can try to understand how mana is dependent on their separation distance. So we cannot just simply go back and use the naive counting tensors using the past domain dependence, because they don't share any tensor in the past domain dependence. Nevertheless, there is a coarse-grained version of them that do share a tensor in the past domain dependence. This is this one. So you can think of first their coarse-grained version. So this guy, the red guy, has some mana. Let's call this coarse-grained version rho k sub 0. Now this coarse-grained version is in fact related to the fine-grained version by RG in this tensor network, right? So for example, for each layer, you can just apply. So to get from here to here, you just apply isometry, then partial trace, and you apply disentangular, then partial trace at each layer, and so on and so forth until you get to where you want. So what it looks like in terms of a quantum circuit is the following. You started with the coarse-grained reduced density matrix, then you just apply the circuit over and over and over again for each layer. And then eventually it will take you to a fixed point, a large layer, right? So that's sort of how MERA works. So in fact, you can look at this with a bit more detail. So you can expand this. you can look at the eigenoperators of this quantum channel. So they have a set of eigenvalues. The one with the dominant eigenvalue is going to be the one that's left over in the large layer limit, right? So that's going to be the fixed point. But there's like subdominant eigenvalues. Let's call it lambda 2, right? So this is the one that's going to decay over a number of layers. And if you look at For example, this is the coarse-grained red blob, right? This is the state that has some mana to start with, and this is probably the fixed point that you will eventually get to in state space. And the blue pentagon denotes the cone of stabilizer states, right? And let C be the distance between these two states. Then suppose lambda 2 is like order 1/2, then every time you apply this channel, you move the state closer to the fixed point by this amount. And so this is after 1 layer, and after 2 layers, you get even closer and closer. So the distance between these two states is governed by this C lambda to the delta K. All right. But now if you want to actually compute magic, instead of computing the distance between this state and the fixed point, you really should be computing the distance between this state and the closest state that's in the stabilizer cone, the convex solid stabilizer states. So so the shorter distance here in this picture, it's obvious, right? You really need to subtract the distance between the fixed point, and the boundary of this this cone. And hence, there's an offset by an amount b. You can look at this and then massage it. You convince yourself that delta x, the separation between these UV kind of sites, is really related to the delta k number of layers through a log. Then you remassage this expression, you will get reproduce exactly the thing that we see in numerical results. Right. So really, this 0 at the end is related to the fact that you've entered the stabilizer cone, the convex solid stabilizer states. That's why you get exactly 0. So just to summarize, what we learned is that magic, well, is important. We learned some concept about magic, how to examine it in systems. And what we found is that simulating a CFT requires a lot of resources in terms of magic. In fact, it scales volumetrically. So this is probably bad news if you want to simulate CFT, but then on the other hand, it's also good news, is that suppose you prepare a conformal field theory or in an analog system, and you can swap out the subsystem states, then they contain a lot of magic. So perhaps you can use them to implement T-gates. We also learned that magic is not locally distributed in a conformal field theory. So in fact, if you believe the MERA picture, about more than half, or around half of it, is distributed on a scale that you cannot remove using, say, 1 or 2 local unitaries. So they are actually really important and cannot be ignored. But on the MERA side, we also learned that the network structure seems to capture a lot of the features about what we see numerically. So it's probably indication that the structure of the network that we write down is probably close to optimum, that you actually need this multi-scale sort of analysis or distribution of magic. And this is also probably good news for us, for holographers, is that the networks that we already have, like the happy code and so on and so forth, they really have the correct structure. What remains to be added is really we need to insert additional T-gates or magic into the perfect tensor instead of having them just being stabilizer states or stabilizer code and so on. So a lot of future work, but I think I'm running low on time, so I'm just going to leave this page on and take questions. Thank you.
Thank you, Charles. We have 5 minutes for questions.
Okay, Charles, I had a question about one of the things that you said on the previous slide.
Yeah.
So do you guys have something in mind for, I guess, an equivalent of magic state distillation for CFTs? Because like it's one thing to say that like the CFT state has a large amount of magic, and I imagine that would in principle be useful for preparing quantum circuits and taking up some of the T-gate costs. But how do you actually extract I guess, the elements of it that are most useful, and like, for example, plug it into a quantum circuit.
We haven't spent a whole lot of time thinking about this. I would imagine maybe some modifications or some versions of Kitaya-Bravi, maybe. If you have the two-side reduced density matrix, they just keep using, I don't know, how you can swap it out, of course, but suppose you can have multiple copies of this, then maybe you can reuse some of the existing protocols you already have.
Well, that would seem to me that would work, but I imagine that it would be highly inefficient.
Yeah, no, we don't have, we haven't really thought of very efficient. Yeah, this is definitely a good direction to think about.
I think that it'd be interesting to think about like leveraging the tree structure of the state to I guess build a more specialized version of Kitaya-Bravi, which can probably do a much more efficient distillation of these magic states, because your magic states are also kind of like localized in this way, right? That's why you could get away with the volumetric counting, because the fact that the different inputs of mana add additively comes from the fact that they get introduced at different scales that commute with them.
That's right. Yeah.
I think it's something interesting to.
Yeah, that's definitely very interesting.
Before we have more questions, I just wanted to make a suggestion. Nobody's, of course, required to turn their video on, but I would encourage it during the question sessions, just because it makes it feel a little more interactive, and I would encourage it, especially for those people asking questions. So unless people are in their pajamas, then this is encouraged.
By the way,
maybe even if they are, I don't know.
I think even during the talk, it will be helpful to have people turning down the video instead. I mean, because the speaker may feel like talking to the wall if there's no one in the video.
Thank you, Xiaolian. Yeah.
More questions?
I see a bunch of hands being raised. I don't know what they...
Yeah, I don't know. I was waiting for the chair to... I have a question. Should I ask it? Or?
Please do, and everybody who is not asking a question, please mute yourselves if you haven't already.
So maybe I missed that, but if I look at a free theory and the holographic CFT with the same center charge, is it true that the free theory has less magic? Maga has less mana?
Does the free theory have less mana than?
Yeah.
Sorry, there's a lot of noise coming from background. So, Xiaoliang, do you mean that the free theory has less mana than, for example, a holographic theory? Is that the question? Now, I don't have. There are several points that I will probably raise here that are extremely speculative. The short answer is I don't know. The longer answer is I don't think it necessarily have to be true. But at least when you, so here's the reasoning. That it seems like these magic are primarily used to sort of tilt the flat spectrum, entanglement spectrum, to something that's more tilted. So you would, at least to some very naive guess, you would think that, you know, I need more magic if you want to make more tilts. Now for the holographic CFT is that we know it's roughly flat, but up to these non-flatness controlled by order G Newton. Now it could be that if I can somehow fix n, the large n, and then I can somehow tune G Newton to be very, 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 very small, then perhaps I can get away with a state that uses very little magic. But then at the end, I also have to be careful about, you know, the relation between, so maybe I cannot get away with small amount of magic because n and G Newton are related in the end. So maybe the large n sort of makes up for it. It's really not clear to me that how much more magic I will have to have for a large n theory compared to a free theory. So right now I don't have, but there's probably along this direction we can look into.
Okay, very good. So maybe no one has more questions. Maybe we should move forward. And let's thank Charles again for his talk. Or Zoom claps as well. So all claps are valid.